Hello students, welcome to this lecture in which we're going to talk about divergence theorem and some preliminary discussion about, before we study divergence theorem, about orientation of closed surfaces. And before we have studied flux across general surfaces, In this lecture, we will be concerned with surfaces that are finite solids or boundaries of finite solids. So in this lecture we will be concerned with surfaces that are boundaries of finite solids. So what would be the examples? The surface of a solid sphere, surface of the solid cube, I said cube, but maybe box is a better word, of a solid box. Or the surface of a solid cylinder. That would be a good example too. Like few examples, right? And such surfaces are said to be closed. Such surfaces are said to be closed and a closed surface may or may not be smooth, Like a box, right, is not really smooth. But what is always true, that parts of it are smooth, all right? So we'll put it like this. But most of the surfaces that we have in applications are piecewise smooth. So what does it mean, piecewise smooth? That just means that they consist of finitely many smooth surfaces joined together. joined together in a at the edges. Like a box, right? For example. And now orientation of these surfaces. We will limit our discussion only to the surfaces that we can assign orientation to piecewise surfaces that can be assigned an inward orientation. So basically this means towards the interior of the solid, or an outward orientation. So that means away from the interior. Right, so basically it's very hard to create a mathematical description of it, but basic idea is really simple. If you have a box, then what you can do with the box, so what we can do is we can so basically from the top surface over here, we can think of normal vector going up, from the side here going to the right, from this side over here going to the left, from here going towards us, and so on and so on, right? Going down from here. So that would be outward orientation. So the idea is relatively clear. So we can consider divergence of a vector field. We can consider divergence of a vector field, which we think of f to be defined at a point x, y, and z by this function here, f of x, y, and z I plus g of x, y, and z j plus h of x, y, and z k as y of vector field. Consider divergence of a vector field. This is our vector field represented or defined, probably define is a better word. Defined as divergence of f is equal to partial of f with respect to x plus the partial of f with respect to y plus the partial of set f. This should be g and this should be h with respect to z. And later on we said that we can also write it as the gradient dot product with f of x, y, and z if we think of gradient as an operator. All right. So we will give a physical meaning to this process, which you have not done before. Physical meaning now. All right, so what is the physical meaning? The theorem, which is called Divergence Theorem. Divergence Theorem or Gauss's Theorem. So it will provide a physical interpretation in the context of the fluid flow. So what does the theorem say? The theorem says the following. Let G be a solid whose surface sigma, and a lot of people for the surface use the following notation: partial of G. It also stands for a surface in a lot of books. So whose surface is oriented outward, then if the field is given by our rule, which is f of x, y, and z I plus g of x, y, and z j plus h of x, y, and z k, where f, g, and h have continuous partial derivatives on some open set containing our solid G, and if n is outward unit vector unit normal on sigma, or we can use partial of g. Again, partial g means surface of the solid. Then what? Then we can say that the double integral that we use to calculate the flux ds is the same as the triple integral over the solid g of the divergence of f dv here, right? And again, if we think of the divergence, we can also think of it as the gradient dot f dv. All right, so what does this theorem say? This theorem says the divergence theorem says that the total flux of the velocity field across the boundary, which is this part, and this boundary is for this solid, is equal to the triple integral of the divergence of the velocity field over the solid. So we stated the theorem. We're not going to prove it because the proof is quite complicated. In most books for undergraduates, it's just some cases are proven. But let's look at a few examples that we can use this theorem for. So first example is like this. Let Q be a solid bounded by the paraboloid z equals to 4 minus x squared minus y squared, and the xy plane the question is find the flux of the vector field f of x, y, and z equal to x cubed, y cubed, and z cubed. So what kind of picture we have in this case? Again, x squared minus y squared. If a factor minus, it's just x squared and y squared. And it's 4 minus this quantity, so basically it's upside down paraboloid. And we achieve value 4 when we plug in x equals 0 and y equal to 0. So basically our picture looks something like this. Our paraboloid is going something like this. And on the bottom we have a circle. We have a circle. So if we plug in z equal to 0, we'll have x squared plus y squared equals to 4. So it's 2 and 2 over here. All right. So this is our Q. This is our Q. And we can try to compute the flux directly. So we must consider two different portions of the surface of Q. Let's use dq for the surface of Q. Right. Why is that true? Because we have this top over here, which is paraboloid itself, and on the bottom we have a circle. So basically the surface of the paraboloid and its base in the xy plane. So this is too hard. You can try it and see that it's going to be too hard. But alternatively, we see that the gradient dot f of x, y, and z will be the gradient that x cubed, y cubed, and z cubed. So basically we just take partials, so it's 3x squared, 3y squared, and 3z squared. Right, as a vector. And I wrote it again incorrectly. It should be plus and no vector sign because that's a dot product, so it's summation. And we can use divergence theorem. So from the divergence theorem, we have we have that the double integral over the surface of Q of f dot n, and which we're not going to calculate any of this. It's just integral over the solid Q. The integral over the solid Q of gradient dot f of x, y, and z dv. Alright, so we continue on, we put everything in, so basically we need to find the triple integral over the solid Q of 3x squared plus 3y squared plus 3z squared dv. And can we switch to the polar coordinates here? Every time on a parallel to xy plane, if we cut this surface parallel to the xy plane, we will see that it will be a circle, right? So that means polar coordinates is good, and the height is just z. The height is just z. So let's try to do that. What we can do, we will factor 3 out. We'll factor 3 out. So it's equal to, then we have a triple integral, and for x squared and y plus y squared, this x squared plus y squared, this is just r squared. Then z is just z, so we don't touch it in polar coordinates. Then since we use the polar coordinates, we have dz, and we have r d. I said dz, right? Then r dr d theta, since we're switching to the polar coordinates. Now we have to trace our values. Our radius on the our radius changing from 0 to 2. So our radius changing from 0 to 2. So we put it for the dr, so it's over here in the second one. Then our angle changes from 0 to 2 pi. And for each such circle that we select, we need to calculate the height. And the height goes up to this surface over here. So it goes from 0 up to the surface. And the surface is 4 minus x squared plus y squared. But again, x squared plus y squared we changed by r squared. So it's 4 minus r squared. And that's our integral. Basically, you start calculating it. You go 0 to 2 pi, 0 to 2, and you have so we do the first integral with respect to z. So we will have r squared z plus z cubed over 3. R is a fixed number, it doesn't change. And we can even probably move it over here, r dr d theta. But this expression we have to evaluate from 0 to 4 minus r squared. But if we plug in 0 for z, this will zero out, so it's not crazy important. And we have 3 integral from 0 to 2 pi, integral from 0 to 2. And we have r squared times r, which is r cubed over here. Then we plug in 4 minus r squared for z plus plus 1/3 from here. Then for z cubed we have 4 minus r squared cubed. We have r, this r, and we have dr d theta. All right. But then it's just a normal calculus problem, so calculus 2 problem, even maybe calculus 1 problem here. This is a relatively easy integral, calculus 1 problem. So I'm not going to do that, but if you actually go through the procedure, you're going to get 96 pi. I used maxima to do that, wx maxima, but again, it's doable by hands. It's relatively easy. U substitution for this part, but here just direct power rule. So that's not hard. So basically, we replaced very messy calculations for this direct flux calculation with a relatively easy calculations through the divergence theorem by calculating relatively simple triple integral. All right, so let's do one more example for this lecture. In this example, we'll try to prove some result. Prove that the flux of the vector field f of x, y, and z equal to 3y cosine of z, x squared e to the z, and x sine of y is 0 over any closed oriented surface dq enclosing a solid region. All right, so let's try to solve it, and solution is relatively nice and easy. So we need to calculate the divergence. The divergence of f is gradient dot f. So it's going to be gradient dot the vector 3y cosine of z, x squared e to the z, x sine of y. So basically we have to take a partial with respect to x of the first component, y cosine of z, plus the partial with respect to y of x squared e to the z, plus the partial with respect to z of x sine of y. But as you can see, there is no x over here, so this is 0, this is also 0, and this one is also 0, so we get 0. And so that means that from the divergence theorem, we have that the flux over the surface of this solid f dot n ds is equal to the triple integral over q gradient dot f and it's equal to the triple integral of 0 over q and it's equal to 0 for any solid region Q. That belongs to the 3D space. Okay, so probably good place to stop this lecture, and I'll see you in the next one.